This is AP Calculus ABA. We're doing Unit 7, Lesson 5, Modeling and Optimization. So we're going to take a look at modeling and optimizing in a particular situation here. So here's the scenario. I've got a sheet of paper that is 8.5 inches wide, 2, 4, 6, 8.5. and 10 inches long, 2, 4, 6, 8, 10. 8.5 by 10. Actually, 8.5 by 11. Let's do 8.5 by 10. 2, 4, 6, 8, 10. Should have done 8 by 10. Why not? Well, we'll keep it the same. 8.5 by 10. So I've got a sheet of paper that's this big, and that's a sheet of stiff cardboard, actually. And I'm going to make a box out of this, a three-dimensional box. And here's how I'm going to do it. I'm going to cut a corner off one end, and I'm going to cut a corner off another end as well. But I'm going to make a box that has a lid. Not an open topped box, but a box that has a lid. Okay, so I'm going to do this here. I'm going to take a corner off. That's x by x. And take a corner off. That's x by x. Okay, and I'm going to take this corner off. That is just the right dimension. It's x this way. Okay, and I'm going to do dotted lines for folding lines here. Okay, and I'm going to cut these rectangles off. Do the folding lines here. And I'm going to do a folding line here. So this is x. But this box top here is going to be the same dimensions as the top of the box here. So y and y. Okay? But this is an 8.5 by 10 inch sheet of paper. Okay, and if I cut this out and fold it, it'll create a box that folds like so. And it'll have a closed lid here. I'm going to do dotted lines for hidden lines here. Okay? And the dimensions are x here for the height, but I don't know the dimensions otherwise here. I can figure out some of them. I know, for example, if I take an x off both ends, that this is 8.5 minus 2x. So that's 8.5 minus 2x. Okay? Actually, that's the long dimension, so 8.5 minus 2x. But this one's a little tougher to figure out. If I figure it out this way, I look at it this way here, there's two y's and there's two x's that together make 10 for the vertical height. We can factor out and divide by 2, y plus x equals 5, and y is 5 minus x. So let's replace the y with 5 minus x. So this dimension is 5 minus x. Okay? So we've got an x by 8.5 minus 2x by 5 minus 2x box. Okay? All of that is cut out of an 8.5 by 10 inch sheet of paper. And I'm curious what the dimensions are that we're going to maximize the volume. If I make x very small, it's going to make a short, flat box. If I make x very large, it's going to make a tall, skinny box. Okay, and we are certainly limited. We certainly can't go past about 4. If I went 5 inches for the width of the box, for the value of x, that itself would make up 10, and we'd have nothing left over for the y's. Okay, so it wouldn't make sense to go past 5. All right, so let's take a look at an expression for the volume of the box. The volume is length times width times height, so x times 5 minus x times 8.5 minus 2x. We now have an expression for the volume of the box that is based on just the size of the square that I cut out of the sheet of paper. And this is a good example of an optimization problem in which now I want to find out what size should I cut that square out to maximize the volume, to make the volume as high as possible. Okay, and so this is a maximization problem of finding a local maximum or a global maximum, if you please. We are going to let x be on the domain from 0 to certainly no bigger than 5. It can't be bigger than half of 8.5 actually, so 4.25. Okay, so it could possibly be that 0 would be or 4.25 would be critical values as well. In this case they're not. If it has no width, it's going to have no volume. So, and if I don't cut a square out, it's just a flat sheet of paper and then doesn't hold anything, it has 0 volume. So it's going to have 0 volume at both of those values. Okay, but we're interested in where it maximizes in between. So let's go about finding the critical values. Well, let's multiply things out. X times 5 times 8.5 is 42.5. Minus 5 times 2x is 10x. Minus 8.5 times x plus 2x squared. A little combining of like terms here. X 42.5 minus 18.5x plus 2x squared. Distribute. So 42.5x minus 18.5x squared plus 2x cubed. Okay, and now let's take the derivative, and I'm going to reverse the order of the terms as well. 2x cubed derivative is 6x squared minus 18.5 times 2 is 37 x plus 42.5. Okay, and we have a quadratic, and remember a critical value occurs where the slope is 0. So we're going to set this equal to 0, and we're going to find out what x equals. So I'm going to bring up Desmos. Okay. All right. So Desmos, here's the way I like to do quadratics in Desmos here. I just say a equals 6, b equals 37, and c equals 42.5, but b actually is negative 37, not positive 37. Okay, and now just enter the quadratic formula. Negative b plus or minus square root b squared minus 4ac all over 2a, and I get 4.64. That's actually outside my domain, 4.64. So that's going to be a toss-out. And minus 1.53. Okay, so we're going to toss that out. But 1.53 appears to be a maximum. Now I can test the second derivative and see if it's concave up or concave down. If it's concave down, it's going to be a maximum. Let's go ahead and do that here. So v double prime is 12x minus 37, and 12 times 1.53 minus 37. 12 times 1.53 minus 37 is negative 18.64, which is less than 0, which is concave down, which means this is a max. Okay, so we can conclude then that if I cut a corner off at 1.53 inches by 1.53 inches by 1.53 inches, 5.3, 1.53 and 5 minus x, 5 minus x plus x. Yeah, 5 minus x, so this is going to be 5 inches. Is that right? Yeah. Yep. by 5 inches. So these are the dimensions I should cut on my paper. And then fold my box, and it will maximize the volume. We can test or verify this result by graphing the original volume formula. So the volume is x times 5 minus x times 8.5 minus 2x. Okay? And I'm interested in viewing this right here, 1.527. That does match our peak value. Notice what happens down here at 4.64 as we get a volume of negative 1.303, which is also another critical value, but it's outside the the range. So the domain is from 0 to 4.25.